What's up? So we're here doing energy practice problems. So let's go ahead and get into this. All right, so this is the basic introduction to worksheet here. So it should be relatively easy. Hey. All right, so number one says a comet with a mass of 7.85 times 10 to the 11th kilograms strikes Earth at a speed of 25 meters per second. Find the kinetic energy in joules. All right, and one's pretty basic, straightforward, just getting used to the equation. You have kinetic energy equals 1/2 mv squared. It gives you mass, which is 7.85 times 10 to the 11th. You have velocity is 25 meters per second. You need to find kinetic energy. All right, so all you do is plug in Ke equals 1/2 m 7.85 times 10 to the 11th, 25 squared. Okay, so I go ahead and plug it into my calculator. So I do 25 squared times 7.85 second EE 11 times 0.5. And I get 2.45 times 10 to the 14th. 2.45 times 10 to the 14th joules. All right, pretty basic, pretty straightforward. It's just checking to see if you're able to use that kinetic energy equation. Number two is the same thing except for potential energy. Just checking to see if you're able to use the potential energy equation. So let's go ahead and do that. Number two. Number two says you lift a 2 kilogram textbook from the floor to a shelf 2.1 meters above the floor. What is the gravitational potential energy relative to the floor? So I have A. The height is 2.1. The mass of the book is 2. Gravity is 9.8. Find PE. So I have PE equals mgh. Mass is 2. Gravity 9.8. Height 2.1. PE equals. All right, let's go ahead and do that. 2.1 times 9.8 times 2, 41.16. Joules. All right. B says, what is this gravitational potential energy relative to your head, assuming that you're 1.65 meters tall? So now if the shelf here, that's the shelf, this is 2.1 meters, and your head here is 1.65 here, we need to find the distance from there to there, because that's where you're comparing. You're comparing from the shelf to his head. So really all I have to do is 2.1 minus 1.65 gives me that distance there. So I do 2.1 minus 1.65, I get 0.45 meters. So my new height here is 0.45 meters. I still know the mass is 2, and I still know gravity is 9.8. Find PE. PE equals mgh. PE equals mass is 2, g is 9.8, height is 0.45. PE equals 0.45 times 9.8 times 2 gives me 8.82 joules. All right, these problems are pretty easy, pretty straightforward, just using the basic equations here. All right, number 3, a 6 kilogram particle has a speed of 2 meters per second at point A and kinetic energy of 7.5 joules at point B. What is the kinetic energy at point A? Okay, so let's see here. A. It says, what is the kinetic energy at point A? Well, we know the mass is 0.6. Alright, see what else it gives me. It gives me speed of 2 meters per second. Velocity, I know, and I'm trying to find kinetic energy. Ke equals 1/2 mv squared. Ke equals 1/2. Mass is 0.6 times 2 squared. I do 2 squared, which is 4. So 4 times 0.6 times 0.5 gives me 1.2 joules. All right, B says, what is its speed at B? Well, I know it has kinetic energy of 7.5. So kinetic energy here is 7.5 joules. I know the mass is still the same, 0.6 kilograms. I want to know velocity. So I use the same equation. Ke equals 1/2 mv squared. Ke is 7.5, 1/2, 0.6 v squared. So let's go ahead and I'll simplify. So I got 7.5 equals 0.5 times 0.6 gives me 0.3 v squared. I divide by 0.3. I get v squared equals 7.5 divided by 0.3 gives me 25. Square root, I get velocity is 5 meters per second. C says, what is the total work done as it moves from point A to point B? All right, well, work is change in kinetic energy, or change in energy. So work is also equal to Ke final minus Ke initial. Work is equal to kinetic energy final was 7.5 minus kinetic energy initial is 1.2. Work is equal to 7.5 minus 1.2, 6.3 joules. All right, these are basic. You're just using basic equations, nothing tricky here, okay? Just keep rolling here. Number 4, it says a large chunk of ice with mass 15 kilograms falls from a roof 8 meters above the ground. Ignoring air resistance, find the kinetic energy of the ice when it reaches the ground. What is the speed of the ice when it reaches the ground? Okay, so let's go ahead and draw this. Nice little house guy. Okay. Impressive for quick drawing. Chunk of ice is right there. Okay, so the ice, it tells us, is a distance of 8 meters above the ground. It is a mass of 15 kilograms. Okay, so we set this problem up here. So what we're going to use here is the law of conservation of energy, stating that if you find the total energy at any point, it's equal at every other point along its path. So in other words, if I find the total energy, in other words, kinetic energy plus potential energy, at any point up here, I know it at any other point. So what I want to do is I want to start at a point where I know the most information. Well, I know the most information right at the point where it's released. So at the top, I know that it has a mass of 15, it has a height of 8, I know G. Does it make sense I can find potential energy here? It is mgh. Well, I also know that if it releases, its velocity at that point is 0. Therefore, its kinetic energy at that point is 0. So I know that if it released from rest, its kinetic energy at that point is 0. Its potential energy at that point, we got to calculate. Potential energy equals Mass is 15 times 9.8 times 8. PE equals 8 times 9.8 times 15 equals 1176 joules. 1176 joules. So the energy total is equal to PE plus KE at a specific point. So we're at this specific point here. So the energy total for the system comes out to 1176 joules. So now, if I asked you at any point what the energy total was, you'd tell me it's that. So what they want us to do is find information right there. We want to know information right before it strikes the ground. So at bottom. Well, if we're right before we hit the ground, we can take our height is equal to 0. If our height is equal to 0, that means our potential energy is equal to 0. So I know that. Right before it strikes the ground, its potential energy is 0. So that means all of that kinetic energy has transferred into potential energy. Now, if my potential energy is 0, and I know my energy total is 1176, because I found it at that point, so it's the same at every other point, I know that my kinetic energy must be 1176 to make the energy total 1176. So I know, I think that's letter A, it asks you to find the kinetic energy. Let me check. Yeah, kinetic energy. Now it wants to know what the velocity is. So I know mass is 15. I know kinetic energy is 1176, and I want to know velocity. So I use kinetic energy equals 1/2 mv squared. Kinetic energy is 1176 equals 1/2 mass 15 velocity squared. So I get 1176 equals 7.5 v squared divided by 7.5, cancel out. I get v squared equals, we do that, 1176 divided by 7.5 gives me 156.8. 156.8, I square root, I get V equals second square root, second answer, 12.5 meters per second. Okay? 12.5 meters per second. That was the first time we used law of conservation of energy. Okay? Just remember, the key is you need to find the energy total at one point, and then you know the energy total at every single point. And you have to start at the place where you were given the most information. Like we were given the most information right when it was released. Okay? So let's go on here. It says a bike rider approaches a hill at a speed of 8.5 meters per second. The mass of the bike and the rider together is 85 kilograms. Find the initial kinetic energy of the system. The rider coasts up the hill, assuming that there's no friction. At what height will the bike come to rest? So let me draw this picture. Hill, okay, so at the bottom, bike. All right. So at the bottom of the hill, bottom, we can set its height equal to 0, right? That's ground level. Height equals 0, therefore potential energy here equals 0. Right? Now it says it approaches the hill at a speed of 8.5 meters per second and has a mass of 85 kilograms. So I know its velocity is 8.5 at the bottom of the hill and has a mass of 85 kilograms. It asks you first to find kinetic energy. Well, I know kinetic energy equals 1/2 mv squared. Kinetic energy equals 1/2 85 0.5 squared. So I do that in my calculator, I get 8.5 squared times 85 times 0.5. And I get 3070.6. 3070.6 joules. Okay? So I can find the energy total of the system at this point, because I'm observing it right there. So I know energy total is equal to KE plus PE. Well, E total is equal to 3070.6 joules. So now I know that. Okay? The question goes on to ask, if the rider coasts up the hill, assuming that there's no friction, at what height will the bike come to rest? So we're going to go up the hill, and he's going to come to a stop, right? So at that point, his velocity is equal to 0. So at top, velocity equals 0, therefore kinetic energy is equal to 0. I know that. I also know that my energy total is equal to the energy total here, which is the 3070.6 joules. So I know that if I have 0 kinetic energy and that much energy total, that potential energy must be 3070.6. I know the mass is, what was it, 15? No, it's 85. And G is 9.8. I can find H by just using potential energy. PE equals mgh. PE is 3070.6 equals mass 85, G 9.8, H is what I'm looking for. Divide. I do. 3070.6 divided by 85 divided by 9.8. And I get 3.7 meters. All right, that's the height. So again, in this one, you start with all kinetic energy. All kinetic, because you're at ground level. As you go up the hill, you lose kinetic energy, but gain potential energy. Okay? Once you get to the point where the bike rider stops, 0, so you lost all your kinetic energy, but gained it back in all potential energy here. So there is a complete transfer again, just like number 4. All right, so let's look at number 6. This has to deal with springs. It says, to test the force constant of a spring is hung vertically and an object is attached to its lower end. If the spring is stretched by 2 centimeters by a suspended object having a mass of 55 kilograms, what is the force constant of the spring? All right, good. So let's draw this one out. All right, what number is this? 6. Okay, spring with no weight on it is right there. Then I hang a mass and it stretches it out a distance. This is your X. How far you stretch it is X. Okay? In this problem it says we stretch it by 2 centimeters, but remember we have to be in meters, so it's 0.02 meters. I just converted to meters. All right. It has a mass of 55 kilograms. When I think about the forces, what's pulling this block down? Oh, the weight is. Weight is equal to mg. Well, it is also the force of the spring pulling it up. So at the point where it's not moving, so what you've done is you've let this spring down. You've attached the weight, you let it down, and it stops right here. So your hand pulls away from it. And that weight stays right there. So if it stays right there, the weight of the mass is pulling it down and the spring is holding it up equally. Because if the spring was pulling harder, the weight would move up. If the weight was pulling harder, it would move down. But if it's equal, it stays there. So what I know is the force of the spring is equal to the weight when it equals out. So I can calculate weight. Weight is equal to mg. The mass is, what is it? 0.55, it's 0.55 times 9.8. Weight is equal to 0.55 times 9.8. I get 5.39 newtons. equals your weight, and it also equals the force of the spring. All right, so if I have the force of the spring and x, I can use my force of the spring equation, Fs equals negative kx. All right, well, I have to decide. If up is positive and down is negative, delta x is going to be negative, right? Because you go down 2 centimeters. Force of K is what we call the spring constant. Okay? The spring constant tells how rigid it is. All right? Springs that are harder to stretch out have a higher K value. Springs that are easy to stretch out have a lower K value. So this number here describes the stiffness of the spring. So every different spring has a different K value here. So I plug in. Force of the spring is 5.39 equals negative K is what I'm looking for, negative 0.02. All right, so I divide, well, negatives cancel out, I divide by 0.02, 0.02, I get K is equal to 5.39 divided by 0.02, I get 269.5. 269.5 Newton meters. All right, good. That's a basic spring problem. All right, number 7. Number 7 is actually the lab. These are the calculations for your lab that you're going to be doing. All right, you're going to be calculating how much horsepower you generate by running upstairs. So this is a problem where a guy's running up stairs to figure out how much horsepower he generates. So the runner has a mass of 50 kilograms. So mass of the guy is 50 kilograms. Oh, not grams. All right. He runs up the stairs, the Sears Tower, so it goes up a height of 443 meters. He gets to the top, time is 15 minutes. Obviously I have to convert that to seconds, so 1 minute is 60 seconds. I do 15 times 60. I get 900 seconds. So when you think about it, when you run up the stairs, you're going against gravity, right? Well, what is the force of gravity that you feel? You feel your weight, right? So the force you have to overcome is the weight of you pulling down. So the first thing I want to do is calculate this guy's weight by using his mass. So weight is equal to mg. Weight equals mass is 50, g is 9.8. Weight equals. So let's do 50 times 9.8. I get 490 newtons. That's the force. This will be the force you must overcome. All right? That's the force. Now what I need to do is before I can find power, I need to find how much work he's done. So if your basic equation for work is equal to force times distance. Well, the force is equal to his weight, and the distance is the height of the stairs. So work is equal to force, 490, times the height of the stairs, which is 443 meters. Work is equal to 490 times 443, I get 217,070 joules. All right? Now I can find power. Power is how much work you do in a unit of time. So power is simply the work I've calculated, 217,070, divided by the time, which had to be in seconds, which is 900. Power is equal to 217 divided by 900. Oops, I hit 90, sorry. 217,070 divided by 900. 241 watts. All right, so you generate 240 watts by running up those stairs. It wants to know your horsepower. The conversion factor is on your first sheet. It is 745 let's just say 746. So 1 horsepower is equal to 746 watts. So I start with this, 241 watts. I want to get rid of watts, so I put it on the bottom. I know there's 746 watts equal 1 horsepower. So by running up the stairs at that speed, he generates 241 divided by 746. He generates 0.32 horsepower. So these calculations, this calculation is exactly what you're going to be doing when you calculate what horsepower you can generate by running up the stairs, which is going to be the next lab. It is also a competition lab, so it pays to kind of be athletic on that one. So basically all of you are out of luck. So good luck. Okay? 8. What is the potential energy for an 800 kilogram elevator at the top of the Sears Tower? Okay, sweet. All right, this is another basic one here. So let's look at 8. It has mass, so 8, mass of 800 newtons. It has, 800 kilograms, sorry. It has height, 443. G is 9.8. PE. PE, MGH. PE, mass 800, G 9.8, H 443. PE equals. Type this into my calculator. 800 times 9.8 times 443. Whew, big number. Oh, hands. I got 3, 4, 7, 3, 1, 2, 0 joules. 3,473,120 joules. That's the potential energy of that elevator at the highest point in the Sears Tower. All right. 9. Another 4 spring equation. So let's go ahead and look at this. Springs. Okay. 9. A force of 800 newtons stretches a certain spring a distance of 2 meters. Okay. A. What is the potential energy of the spring when it's stretched 2 meters? B. What is the potential energy when it's compressed 2 meters? Okay. So what it gives us is, it gives us a force. It says the force of the spring to stretch it 0.2 meters has to be, force of the spring is equal to 800 newtons. It stretches a spring a distance of 0.2 meters. All right? So if you draw this, sorry, yeah, or whatever. I don't want to do it that way. Which way I want to do it? Okay, if there's a box and you pull the box that way, one way has to be positive, one way has to be negative. So the force of the spring, if I stretch it to here, is always going to be backwards. So the force of the spring is actually negative, and I've moved it, the 0.2 meters, in the positive direction. So I go, force of the spring is equal to negative kx. Well, the force of the spring is negative 800 equals negative k, x is 0.2. So I divide by negative 0.2. I get 800. I get 4,000. K. So we had to find the spring constant first, okay? We had to figure it out because then we know something about the spring and we can apply it to A because it gives me different information that I need K for. All right, so A, it says, well, what's the potential energy if I do that? Well, PE of a spring is equal to 1/2 kx squared. Well, I know K now, so I can solve for it. PES, 1/2, K is 4,000. X is 0.2 squared. So I do 0.2 squared times 4,000 times 0.5. I get 80 joules. B says, what's the potential energy if you compress it, if the same spring and you could compress it 5 centimeters? So now I have the same spring, so I know K is still 4,000. X is now 0.05 meters. It's 5 centimeters. I want to know the new potential energy. So I do PES equals 1/2 KX squared. PES equals 1/2 K, 4,000. 0.05 squared. PES equals 0.05 squared times 4,000 times 0.5 gives me 5 joules. All right. So the key is you probably have to find K so you know something about that spring. Number 10, last one is another spring one. A force of 720 newtons stretches a certain spring a distance of 0.15 meters. What is the potential energy of the spring when a 60 kilogram mass hangs vertically from it? So again, we're switching scenarios here. So if we can find K, we know that about the spring, and we can use that. All right. So let's look at 10. So the first part, you're stretching a spring. This is initial spot, and then you stretch it that distance, positive, negative. All right, so it says a 700 Newton spring force, so the Fs is going this way, because it always wants to go back to equilibrium. Stretches a spring a distance of, so this distance to here is 0.15 meters. Okay, 0.15 meters. If we can find K, we can then apply it to do that. So I know Fs is equal to negative 720. X is equal to 0.15. Find K. Fs equals negative Kx. Fs is 720. Negative 720 minus K times 0.15. Divide by negative 0.15. Cancels out. K equals 720 divided by 0.15, you get 4,800. All right, so you know the K value for that spring. You know the stiffness of the spring. The next thing you want to do is now draw this that we're hanging a mass. So I'm going to hang a mass here. That's equilibrium. Now, once I hang it, it comes to rest right here. It has 60 kilogram mass. I need to know how far it stretches. So positive, negative. The force of the spring will be going that way. Weight is what's pulling it down. And remember that if it comes to rest, the weight pulling it down must equal the force pushing it up. So I know if I find weight is equal to mg, weight equals 60 times 9.8. Weight equals 60 times 9.8, 588 newtons. All right, so I have 588 newtons pulling it down. So to oppose it, it has to be 588 newtons. So the force of the spring is 588 newtons. I know the K value for the spring is the same as 4,800. I want to know X. So I go force of the spring equals negative Kx. Force of the spring is 588 equals negative 4,800 X. Divide by negative 4,800. Cancels out. Negative 4,800. I get X equals 588 divided by negative 4,800. Negative 0.12 meters. That should make sense because it goes down, and down is negative in our drawing. All right. So hopefully that that helps you with those initial problems. and we should be good to go from getting more difficult. We've seen spring problems, we've seen the basic kinetic energy and potential energy, and we've seen some basic law of conservation of energy problems. All right? All right, she says she hopes you guys are doing really well, and hopefully you guys are enjoying class without me, okay? Well, good luck, and remember, number 7 is like the lab you're gonna do. So I do go over the conversion in the lab thing, but I also do it here. So if you have questions, just rewatch number 7 on how to calculate it, all right? Good luck, and see you later.